In this video, questions about water waves are used to demonstrate the four properties of waves: reflection, refraction, diffraction, and interference. Now, question 1. The shepherd and the figure reach a trough at the time t equal to 1 second. The water wave will move towards him from right to left. The trough and the adjacent crash is 10 meters apart in horizontal. The shepherd will just rise from the trough to the crash of 5 meters in 1 second. You're asked to find the amplitudes of the water wave and the speed. Now, the amplitude is measured from the equilibrium position to the top. So, the amplitude should be 5 meters divided by 2 equal to 2.5 meters. Then we need to find the speed. First, we need to find the wavelength and the period. From the figure, we can find that the wavelength is the distance between the two tracks. Okay, and it is equal to 10 meters times 2. Period is the time to move by one wavelength. Now the time to move by half wavelength is 1 second. So period is 1 second times 2 means 2 seconds. Then we can calculate the speed equal the distance traveled by time. That means the wavelength traveled by the time used in 1 period, 2 seconds. So it becomes 10 meters per second. Question 2. In a ripple tank, a few drops of water generate circular wavefront as shown. The wavefront is reflected by a strict barriers. You're asked to draw the reflected wavefront. Now first we look at the center of the circle. It generates the circular wavefront and spread outward. When it hits the barrier, it will reflect it. And then at the same time when it reflected, the barrier will seem to generate a virtual image. Give a measure from the center of O to the barrier and measure the equal distance from the barrier and behind the barrier. We can draw the position of I. And it would generate a wavefront like this. And the wavefront will be seen to come from the I. Question 5. A strict vibrator generates a series of plain water waves in a ripple tank as shown. The plain water wave travels from region A to B. The wavelength in region A and B are 4 cm and 3 cm respectively. You are asked to find which region is shallower. The wave speed depends on the depth. That means when the water is deeper, it will travel faster, but when it's shallower, it will travel slower. And the speed is also equal to F times lambda. In both regions, they are traveling in the same frequency. So FA equal to FB. But in A, the wavelength is longer. So that means A have a greater speed in B. So in region B, it is travel slower, so region B is shallower. Now, from part B, you are asked to find the refractive index when the wave travels from A to B. Now let's use the N from A to B to represent the refractive index. And it is equal to the ratio of the wave speed between A and B. And also lambda A over lambda B. That means 4 cm equal to 3 cm equal to 1.33. In part C, you are given that the theta A here is 20 degrees and you are asked to find the theta B. Then we have to use the refractive index again because it can also calculate it by sine theta A over sine theta B. So we have 1.33 equal to sine 20 degrees over sine theta B. Then we can find theta B is sine inverted sine 20 degrees over 1.33. So it is equal to 14.9 degrees. We come to question 4. Figures shows a series of plain water wave, and travel towards a gap. This is a gap. The wave exhibit diffractions. Means that when the wave passes through the gap, the wavefront will spread outside the size of the gap. Now assume the depth of water remains unchanged. You're asked to find out what happened to the diffraction due to the following change. First, we have to remind that the degree of diffraction depends on the relative size of the gap and the wavelength. That means when the gap relative to the wavelength decreases, the diffraction will increase. So in the part A, when the gap is narrower, the degree of diffraction will increase. Then we go to part B. It's a little bit complicated. Okay, we're asked what happened when the frequency increases. Okay, go back to the depth. The depth is unchanged, so the wave speed also remains unchanged. By the equation V equal to F lambda, when the frequency increases, the wavelength will decrease. So relatively, the gap is increased relative to the wavelength. Okay, not the gap increase, but the wavelength decrease. So relatively, then we will find that the diffraction will go to opposite. That means it will decrease. Now we go to part C. What happens when the aperture is largest? Actually, the aperture does not affect diffraction. So when the aperture is largest, the degree of diffractions does not change. For question 5, in a ripple tank, a circular water wavefronts are produced by two vibrating dippers, P and Q. The dippers are vibrating in phase. The separation is 4 lambda, where lambda is the wavelength of the waves. Figure shows the wavefront at certain moments. The circular line represents the crest of the wavefronts. Now you are asked to draw and label lines in the figure, connecting all the points R which have the path difference 1 lambda and the path difference 0.5 lambdas. Now let's start for the more easy one. We join the lines which have 0 path difference. That means the middle point. So this 3 point here is the middle point between Q and R. So we join it together. It represents the path difference is 0 from P to Q, and usually I will label in A0. Now we can try to draw a line which the path difference is 1 lambda, which is next to A0. Yeah, we connect this point. These 2 points have the path difference from P to Q is 1 lambda. So joining this, we have A1. And on the other side of the A0, we can also draw another A1. Now we need to draw the line which have path difference 0.5 lambda, okay, which is between A0 and A1. And I draw here, this is N1, N1. Now you're asked to describe what happened to the lines N1 and A1 if the separation between P and Q is increased. That means I move P and Q slightly outward. Then this line will be close together. So the separation between N1 and A1 will decrease. Now we go to part B. The figure shows the side view of the water level along the line A1 at a certain instant. You're asked to sketch on the same figures the side view of the water level at a time a quarter of t later, where t is the period of the water wave. After a quarter of t, the whole shape of the wave will move to the right at a quarter of wavelength. That means we can, here at the beginning, it's the drop, and it will move to a quarter. So it will become here. And the crash here will also move a quarter. So the crash here. Similarly, the whole waveform will move to the right by a quarter of wavelength like this. Now for part C, X is the point on the ripple time as shown. You are asked to state the kind of interference that occur at X and also give the reason for this occurrence. Now we have to consider the path difference at the point X from the sources. Okay, now if I'm from P, I go to X, I have to move 1, 2, and 3 lambdas. If I go from Q to X, it needs 1, 2, 3, 4.5 lambda. So the path difference at X should be equal to Qx minus Px. And the distance of Qx is 4.5 lambda and Px is 3 lambdas. So the difference is 1.5 lambda. That means when the wave reach at the point C, they have out of phase. So destructive interference occurs at point X. Okay, we go to part D. What's the change on X if the source P and Q are vibrated in antiphase? As the source vibrated in the antiphase, so at the beginnings, it is equivalent to a half lambda path difference between them. So when the wave reaches the point X, the equivalent path difference is the original one, Qx minus Px plus half lambdas. So it will become 4.5 lambda minus 3 lambda plus 0.5 lambda. So it will become 2 lambda. Then the interference will change to constructive interference.